This is the third lecture in the series, and the first two have been fantastic, and thank you for your continued dedication to the idea of this, of getting to 350 and solutions. It's a great honor for me to briefly introduce my Middlebury colleague, Rich Wolfson. He's been teaching in environmental studies and physics since the late 70s at Middlebury.
Mm-hmm.
Rich?
Long time.
A long time, he tells me. And as you can see here, he's the Benjamin F. Wissler Professor of Physics. He is a distinguished teacher, a very distinguished writer, and an active publisher. He's really a role model for many of us in terms of how to embrace the life of a liberal arts professor. There are so many of his books that I can't begin to name them, but I will say that his latest, Energy and Environment and Climate, is about to come out in its second edition. I believe that's Cambridge University Press, right?
W.W. Norton.
W.W. Norton. It's a great book, and it's one of many of his. So Rich is going to talk to us about understanding 350. What is this target we're all talking about? And it's a great pleasure for me to introduce Rich.
Thank you, John. Well, when John mentioned solutions and the fact that he was doing a special issue, I immediately saw an opportunity, and the opportunity is to be the educator that I am about this number 350. John said, millions of people know that number, and I said, yeah, John, but how many understand where it comes from? I think the millions who know that number know it's millions of what? Parts per million of carbon dioxide, parts per million by volume, by the way, if you want to get precise. But where does it come from? And having just given a final exam in which in my climate change course at Middlebury last spring, in which the main final exam question was to interpret a key graph from Jim Hansen et al.'s paper, which introduced the idea of 350, I jumped at the opportunity first to do a piece for Solutions about understanding 350, which I understand will be not sort of an article, but a kind of graphical thing. And then I also jumped at the opportunity to speak to you here about understanding 350. So my goal here is, first of all, to give you, this is not a general talk on global warming or anything like that. In fact, last time I spoke in this room, Tom, you were there. Tom, I saw you somewhere. I gave a talk about, my sort of general talk about global warming. But I'm going to give you a rather narrowly focused exploration of this paper that Jim Hansen and a number of colleagues published in the Open Atmospheric Science Journal in 2008. And I happened to have the privilege of being at the American Geophysical Union meeting in San Francisco when Jim first introduced this idea and gave the public lecture there that became the kernel of this idea. Here's the headline of the paper, the heading of the paper, and I have the paper with me, and it's available to anybody if you just Google it. And it's quite a readable paper. So even if you're not used to reading scientific papers, most of what's in this one you can read without your eyes glazing over and seeing lots of equations and Greek symbols. And it's an important paper and well worth reading. And I want to take you through it. If you really get serious about it, there's also a supplementary paper that contains a lot of supporting material and a lot more graphs and data than is in the main paper itself. So I'm going to be describing this paper, talking about what this paper has to say. And I'm going to give you, in particular, I'm going to start by giving you some science concepts that you need to understand 350. Now, I don't know this group. I don't know how many of you are involved in sort of scientific studies. So I may be going at too elementary a level for you. Holler if you know all these concepts. But I want to introduce a handful of really important science concepts that without understanding them, you won't understand this paper. So that's my goal at the beginning. And then I'm going to talk a little bit about alternatives to 350. Because 350 is not some magic number that everybody agrees with. There's a lot of uncertainty in it. There's a lot of assumptions that go into it that may or may not be correct. And I'm going to raise the question just briefly at the end about possible solutions to the problem we face, since this is, after all, the solutions series. So what are our goals as a society when we're confronted with the problem of global climate change, and particularly global climate change caused by greenhouse gases? Because 350 is ultimately about a greenhouse gas, carbon dioxide. So we have societal goals. Those societal goals plug in my view, to science. And science then, is that my computer or somebody else is making that noise? I hope it's not mine. And then science comes along, and science is going to give us quantitative targets, of which 350 parts per million is a quantitative target. So that's sort of my picture of how this whole process works. We as a society put forth goals. We need science to tell us what numbers we need to achieve then to reach those goals. So in the case of climate science, the quantitative goal was laid out when the UN Framework Convention on Climate Change in March 1994, Article 2 says, the goal is to, quote, prevent dangerous anthropogenic interference with the climate system. And I suspect all of you have heard that phrase. So we've known about this for a long time. For, we're approaching 15, 20 years on this, 16 years. But what is dangerous anthropogenic interference with the climate system? What exactly does that mean? Well, if you listen to the Copenhagen deliberations, John was there, some others probably were there, the general consensus was we need to hold the temperature rise, the global average temperature rise, to something like 2 degrees Celsius above the pre-industrial level. Hansen wrote a paper in 2007, not the paper I'm talking about today, but a previous paper in which he argued 2 degrees was too much, it had to be 1.7 degrees. Notice that at the time, at the year 2000, we were already 0.7 degrees above pre-industrial. So Hansen says we can have at most 1 degree more warming. Now, if you read Hansen's new book, Storms of My Grandchildren, he'll tell you that 1.7 is now, he now considers a prescription for disaster. So those goals, both of them, the Copenhagen goal and the Hansen goal, are considered by at least some people, including Hansen, to be well above what we should be achieving. The island nations at Copenhagen were arguing for 1.5 degrees. And then Hansen in 2008 doesn't give a number in this paper I'm going to be talking about today, doesn't give an actual number for the temperature rise, but he said what we have to do is preserve the stable climate of the Holocene. The Holocene is the period we're now in, the post-glacial period, the current interglacial maximum, as it's called, although Hansen will argue it's no longer an interglacial because he says there will never be another ice age because human beings have taken control of the climate. So that's the goal, preserve a stable climate. And that goal is going to involve something like temperature rises that certainly don't exceed 2 degrees Celsius on the average and maybe have to be lower than that. By the way, what are the IPCC projections for end-of-century climate change? Do you know what the sort of the range is? Anyone know what the range is? What do you think? What's that? Well, 3 point something is maybe the average, but what's the range? I mean, there's a lot of uncertainty about this. You know what the range is? It's like something like 2 to 7, 1.5 to 6, something in that range. So almost all of that range is above these numbers of the IPCC projections for the temperature rise we're going to have experienced by the end of the century. So that's where we're aiming. And we're going to turn that somehow into 350. That's the purpose of this paper. So we're going to have science. We're going to start with science here. And I want to talk about half a dozen science concepts that you need to understand in order to read and understand Hansen's paper. First concept is energy balance. Second is the greenhouse effect. You've all heard of the greenhouse effect. If I asked you to describe the greenhouse effect, I think, who'd like to try? Anyone want to try to describe greenhouse effect? Well, we'll come back to it. I want to talk about the concept of radiative forcing, a more technical sounding term, but I'm sure you've all heard the term forcing. I want to talk about climate sensitivity. That's an important number. I want to talk about feedback effects. And I want to then look at paleoclimate and how we reconstruct the climate of ancient times. So those 5 concepts and then the paleoclimate reconstructions, I want to take you through those in a little mini science lesson here. Then we're going to apply those ideas to see where Hansen comes up with 350. So that's my outline here. So let's begin with energy balance. So right now we're sitting in a comfortable room, temperature 68 degrees Fahrenheit or something. Temperature outside in the Vermont winter is 20 degrees Fahrenheit today. How come the room is warm? After all, we don't have perfect insulation here. We got walls. Heat flows out through the walls. So what's happening? Why isn't it getting cooler in the room? Hello? What do you think? Why isn't it getting cooler in here? What do you mean you don't know? Come on, what's the University of Vermont paying for to keep it warm in here? Heat, right? We're supplying heat to this room. And guess what? If the temperature, if the heat went off, what would happen? It would get cold. Why? Because heat would flow out through the walls. So what do you think about the rate at which the University of Vermont has to pay for and supply heat to this room versus the rate at which it's going out through the walls? What do you think? What do you think about that rate? We got to supply heat to this room at a certain rate, and heat is going out through the walls at a certain rate. And if the temperature stays the same, guess what about those two rates? They're the same. That's the idea of energy balance. And that same idea applies to a planet just as it does to this room. And the idea is that the incoming solar energy, which is the heat that the planet gets, is balanced by the outgoing heat flowing out. Well, we don't have walls on the planet, and since the planet is surrounded by empty space, which doesn't allow heat to flow through it except by the process of radiation, the incoming solar energy is balanced by outgoing infrared radiation. That's the idea of energy balance. So in comes sunlight, by the way, at a colossal rate, at roughly 10,000 times the rate at which human beings use energy. So if anyone ever tells you solar energy is a pie-in-the-sky thing of tree-hugging environmentalists because there isn't enough of it, they're dead wrong. Solar energy provides 99.98% of the energy coming to planet Earth, and it comes at a rate about 10,000 times as great as the rate at which industrial humankind uses energy. There's plenty of solar energy. In it comes, it heats up the planet. Like any object that's warm, the planet gives off energy. In this case, it gives off energy in the form of invisible infrared radiation. We can't see it. It's not as dramatic as sunlight, but it better be giving off infrared radiation at exactly the same rate as sunlight is coming in on average, in order for a stable climate, in order for the temperature to stay the same. Just like in order for the temperature in this room to stay at 68, we got to be bringing heat into the room at the same rate it's flowing out through the walls. That's the concept of energy balance. In a stable climate, we have this balance between incoming solar energy and outgoing infrared. Now, to be sure, the balance varies a little bit. The seasons change. It goes up and down a little bit. But on average, over time, these things are in balance when the climate is stable. That's the first of my science concepts. And by the way, although this is sort of a formal lecture, any questions, anytime, ask them. Anybody got a question about energy balance? Could you go home and tell your parents what energy balance is? Yes, right? It's a very simple concept. If you want to maintain a system at a constant temperature, the energy coming in got to equal the energy going out. Yeah, Bob.
So you often hear that we have all this solar energy coming in at different times of the
Yeah.
industrial use of energy.
Yeah.
That ignores the relative quality of the incoming sunlight versus the stored fossil fuels, which have been concentrated and are a much higher quality form of energy. To concentrate that sunlight, you have to build solar collectors. You have to invest a lot more energy. So it's kind of a
I disagree with your use of the word quality. Thermodynamically, sunlight from an object at 6,000 kelvins is very, very high quality energy. It's much higher. It is. Okay, so let me get the words right. It is high quality energy. It's much higher quality energy than the energy in fossil fuels, which you have to burn and put through inefficient thermodynamic processes. It is diffuse, is the word. It's diffuse. Okay, diffuse.
It makes it less useful. It's not a useful comparison to compare the number of BTUs in the sunlight with the number of BTUs that we consume in fossil fuels.
I would disagree. No, I don't think so. I would disagree with you, with the exception of our use of fossil fuels in transportation vehicles. Other than that, I would disagree with you, because we'll talk about that later. I would disagree. Of course, the fossil fuels are themselves concentrated solar energy. They are more concentrated. I agree with you. They're more convenient in some sense. They may be more economically easy to use right now, although I would, we could argue about that and about whether the externalities are accounted for and all those things you guys know about. So I would slightly disagree with you, and I will be glad to argue about that later. Okay, one concept, right? So if we really look at that energy balance a little bit more quantitatively, anybody who takes a course from me in climate science, this is the first calculation they do. On average, that sunlight is coming in at the rate of about 240 watts, about 2,500 watt light bulbs worth on every square meter of Earth's surface. That accounts for night and day and clouds and all kinds of other stuff. And we physicists know exactly the way things emit infrared radiation or any kind of radiation, and it goes like the fourth power of the temperature. And never mind all these details, but if you calculate, if you set that number for the sunlight coming in to that number for the infrared going out with the temperature in it, you solve for the temperature, you get 255 kelvins. That's 255 degrees above absolute zero. That turns out to be about minus 18 degrees Celsius, or about 0 degrees Fahrenheit, ought to be the temperature of the Earth. Now, here in Vermont in the winter, there are days when that's the temperature. But does it make sense that the temperature on a pretty cold day in Vermont is the average temperature of the whole planet? No. So those numbers are a little bit low. Not dramatically low, but a little bit low. Why are they low? They're low because of the greenhouse effect. And the greenhouse effect results because the Earth has an atmosphere. And the atmosphere is primarily oxygen and nitrogen, which are basically transparent to visible light coming down and transparent to infrared light going out. But it also contains trace amounts of other gases, particularly water vapor and carbon dioxide, that are not transparent to infrared going out. They are transparent to visible light coming in. They're not transparent to infrared going out. That has to do with the molecular properties of those molecules. If you're at all curious about that, just notice that water vapor and carbon dioxide are triatomic, H2O, CO2, versus oxygen, O2, nitrogen, N2. It's that difference that partly makes them responsible for absorbing outgoing infrared radiation. So here's the atmosphere, here's the infrared radiation. The infrared radiation gets absorbed by these greenhouse gases. The greenhouse gases radiate some of it back to the surface of the planet and makes the surface of the planet warmer than it would be otherwise. That's the greenhouse effect. And that occurs naturally. It occurred long before we human beings began dumping carbon dioxide into the atmosphere. And the natural greenhouse effect, caused primarily by water vapor, but also some carbon dioxide, warms the planet by about 33 degrees Celsius. That's about 60 degrees Fahrenheit. Makes it warmer than it would have been otherwise. So we have a nice, habitable, comfortable planet that is at a nice average temperature of about 60 degrees, which sounds a bit better for an average temperature because of this natural greenhouse effect. So we ought to be glad about the greenhouse effect. The planet would not be unlivable without it, but it sure is a much more comfortable place to live. So that's the greenhouse effect. It's a natural greenhouse effect. If we put more greenhouse gases in the atmosphere, the simple physics behind this tells us that we should expect increasing temperature because we'll block more of that infrared going out. There are actually 3 different ways to understand the greenhouse effect. I describe them all in this book, but this is sort of the mid-level of sophistication. Now, this picture I'm giving you is not really, it's pretty simplified. It treats the Earth as almost sort of one point. If you want to look more at the details, and I'm not going to spend time on this, but again, my climate courses do spend a lot of time, you can think about the incoming solar radiation. You think how much gets reflected by clouds, reflected by the surface, absorbed by the surface. You can think about the greenhouse gases up here absorbing infrared, and here they radiate infrared back down to the surface. The surface gets a lot warmer than it would be otherwise. It's got to get rid of that radiation. Everything's in balance. Some energy is carried up by a rising warm air, by the process of transpiration from plants putting water vapor in the atmosphere, by the process of evaporation, blah, blah, all kinds of processes going on here. You go to a climate conference, scientific one anyway, and almost everybody shows this picture at the outset. This is sort of a more detailed picture of Earth's energy balance. Now I want to move to this concept of radiative forcing. Third of the big science concept. Radiative forcing is if we get out of balance. We talked about energy balance, but what if we're not in energy balance? If we're out of energy balance, then there's an imbalance between the upward and downward energy flows. To get scientific about it, it's usually taken by climate scientists to be an imbalance at the junction between the troposphere, the lower level of the atmosphere, up to about 10 to 20 kilometers, where all the weather takes place, and the stratosphere. There are technical reasons for that I won't bother to go into, but that's usually where climate scientists talk about it. So when we're in energy balance, there is as much energy coming down across the tropopause, across that border, as there is going up. And if we're out of energy balance, then we're either heating up or cooling down. Heating up if there's more energy coming in, cooling down if there's more energy going out. It's measured in watts per square meter. If I had more time, I'd get my hand crank generator out here and we'd all understand what a watt is, but I don't have more time. But a watt, you know what a 100-watt light bulb is? A watt is 100th of that. It's a rate of energy use or energy production or whatever. It's measured in watts per square meter. Watts per square meter. That's a big, important number. I was so pleased. I'm going to dump on John for a second. Sorry, John came in and gave the final visit in my climate class last year. He said, you know, don't get too carried away by the science. You know, it's not the only thing that's important. And one of my students stood up and she said, after taking this course, I really understand what a watt per square meter is, and I was so proud of her. Because this is an idea you really need to get a feel for. Climate scientists sort of average this over the whole planet, and they talk about what's happening on a square meter instead of what's talking to the whole planet, because the numbers are more manageable. It's an approximation. It neglects differences among different climate-changing mechanisms. For example, if the sun gets hotter or brighter and dumps an extra watt per square meter into the Earth's system, that has the same effect, according to this forcing concept, as if more greenhouse gases went in the atmosphere and blocked 1 watt per square meter going out. Now, in fact, there are measurable differences in those two effects. That's one way we can tell today's warming is caused by the greenhouse effect and not by the sun getting brighter, for example. but the radiative forcing approximation neglects those differences and is just an approximation, but treats all things that upset that balance in exactly the same way. Why is it called radiative forcing? It's called radiative forcing because if you look again at this diagram, the energy flows high in the atmosphere involve only radiation. That is, the radiation from the sun. I'm not talking about nuclear stuff like you get from tritium that's leaking into groundwater. I'm talking about electromagnetic radiation in the form of visible light or infrared. And up here high in the atmosphere, that's all you've got. Down at the surface, it's more complicated because you have these other processes, convection and transpiration, evaporation, which are not radiative processes. So if you hear someone talking about radiative forcing, RF, that's why they're using that term. This is probably the iconic graph from the IPCC 2000 report. I don't know if any of you have read the IPCC 2001 report, that the iconic graph there was Michael Mann's hockey stick graph. Well, this is the one that sort of appears and plays the most role in the IPCC 2004 report, and it's all about radiative forcing, RF values in watts per square meter. And what you see here, and I'm not going to spend a lot of time on this one, what you see here are different forcing agents. Anthropogenic CO2, human-produced CO2, with the biggest single forcing. Anything to the right is positive forcing, means it causes more energy to come in than goes out, and it means it causes a warming. Anything to the left causes a cooling. It means more energy goes out than comes in. These are cooling effects due largely to sulfate aerosols, largely resulting from pollution from coal-burning power plants that have a cooling effect. You put it all together and we get a net forcing which is somewhere, according to IPCC, between 0.6 and 2.4 watts per square meter positive. That's what's causing the warming. Hansen would tell you that number is closer to 0.5 to 1 watt per square meter, but we can quibble about what it is. It's positive. So today there's an energy imbalance. It's somewhere, according to Hansen, on the order of 0.5 to 1 watt per square meter. And if you want to look at what it means for this diagram crudely, it means that these numbers change. A little less is going out, and particularly a little less is coming out of the surface and escaping to the atmosphere, through the atmosphere to space, because we've got more greenhouse gases. Now, really all the numbers should change a little bit, at least all the ones associated with infrared. So that's sort of crudely, but the main point is what's going out and what's coming in. 342 coming in, but 107 of it gets reflected. That leaves 235. Should have 235 going out. We've only got 234 going out right now. So the Earth is in energy imbalance, and it's a state that we could not maintain for a very long time. Thousands of years. If we did, the planet would get hotter and hotter and hotter and hotter. So we have an energy imbalance today due to radiative forcing, due largely but not entirely to anthropogenic greenhouse gases. Okay, climate sensitivity, next big concept. Climate sensitivity talks about how the planet responds to forcing. You tell me how much imbalance we have, and I want to know what the temperature is going to be. Unfortunately, there are two definitions, and I've got to give you them both. The IPCC simply says climate sensitivity means what would happen if we doubled pre-industrial CO2. What would happen if we went from 280 parts per million, which is what it was pre-industrial, to 560 parts per million? What would happen? The number that comes out of that in a temperature rise is the IPCC's definition of climate sensitivity. The corresponding forcing for doubling CO2 is about 4 watts per square meter of imbalance. We've now got 0.5 to 1 watt, so it's about 4 times what we got now. And the IPCC estimates suggest that the climate sensitivity is about 2 to 4.5 degrees for a doubling of CO2. I asked you earlier what the range was. Somebody said, I said 2 to 7 or something like that. Well, the narrower part of that range is about 2 to 4.5 degrees. The 3 you often hear is about in the middle. Hansen, in his paper, claims that sensitivity is 6 degrees, twice as big as the IPCC reported it to be. Off the top of the scale of the IPCC range, 6 degrees C for a doubling of CO2. There's another definition which is a little more physically meaningful. Instead of talking about a particular happening, like doubling CO2, you simply ask, if I give you a unit change in forcing, 1 watt per square meter change in forcing, what will the temperature change be? Hence IPCC, it's about 0.75. That's about a quarter of this third, which 3, which would happen if you had 4 watts per square meter. Hansen paper, it's about 1.5 watts per square meter, again, about double. So these are two different definitions of the same quantity, measures of how the Earth's climate responds to this energy imbalance. That's the Next to last of my big science concepts before I get to paleoclimate reconstructions. Then there are feedback effects. What's a feedback effect? You get a lousy grade on an exam and you study harder because of that. And your grade goes up. That's negative feedback. Negative feedback because you got a bad grade and so then you did something to make your grade worse. You get a bad grade on an exam and you get so discouraged you go out and you drink all night and you blow the next exam. That's positive feedback. You did bad on the exam and something happened that made you do even worse on the next one. A feedback effect is simply an additional change in a system that follows from some earlier change. And it can be positive if the additional change enhances the original. It can be negative if the additional change diminishes the original change. And the climate system is replete with feedbacks, both positive and negative. Here's an example, a really important example of a positive feedback. This feedback is the reason the Arctic is experiencing much more warming than the rest of the planet, including, by the way, the Antarctic. It's a positive feedback. It's called ice albedo feedback, and it links Earth's surface temperature, the amount of ice cover on the Arctic Ocean particularly, sea ice cover, the reflectivity of the planet, how much sunlight it reflects back into space. It's also called the albedo, and the solar energy absorption. They're all linked. Suppose something happens that increases Earth's temperature a little bit. Well, as a result, we're going to decrease the ice cover. We're going to melt some ice. As a result of that, because ice is very shiny and reflects a lot of sunlight, we're going to reduce the amount of sunlight reflected into space. We're going to therefore increase the amount of sunlight that gets absorbed by the Earth's system, and that in turn is going to increase the Earth's temperature. There's a positive feedback. And by the way, it isn't so much that the temperature went up, it's that the initial effect was reinforced. If you initially cooled the Earth, then you would get more ice and you would get more reflectivity.